Swayam Prabha. Digital India. Educated India.
So, we were talking about mostly turbulence modifying the particle settling velocity, like particle going into upwelling region, downwelling region, etc. But what I was talking about was, imagine very fine particles which fall down very, very slowly. Okay. But imagine that you have a bucket and there is a blob of just fluid filled with particles. Okay. That volume is now heavier, not because one particle, but there are collection of particles in there. So, that blob of particle laden fluid surrounded by other fluid will fall down faster because it is heavier than the surrounding fluid. Its settling velocity will be much larger than that of individual particles, because this is the collective action of particles. And that is what I was talking about, is two-way coupling, in the sense that the particle laden fluid is heavier than the surrounding fluid. Now, on the first day I talked about a simple example. Imagine that you have a tank filled with water, and let us say you have a gate, and behind the gate you have the same water, but you mix in sand or silt. Okay, sand settles too fast, so something very muddy, silt, just 1% volume fraction or something. So, the density is now different by tiny little amount, because silt and sand are 2.5 times heavier than water. So, if you have only 1% by volume, density is higher by 0.2% or 0.25%, very little. Okay, it is almost water. But now when you lift the gate, that fluid is going to go very fast. So, the point is, when a sediment laden or multi-phase region, even if it is heavier by fraction of a percent, that little difference in density is big enough to turn around. So, in other words, heavy fluid will fall down and the lighter fluid will go up. It is sort of like water on top of oil kind of stuff. So, heavier stuff wants to sink down very, very fast. So, in the river context, what I was talking about is that, let us say a muddy layer of water, when it is perfectly flat, it will not fall down fast, because who wants to go first, because nobody can beat the other. And this is where the Rayleigh-Taylor instability comes. In other words, if you give it a little perturbation, the heavy fluid in wherever it's down, it will pull down and it will go very, very fast. That is what I was talking about, two-way coupling effect, is that when you have regions of lighter fluid, heavier fluid because larger volume fraction, slightly larger volume fraction, lighter fluid, heavier fluid. In other words, when you have spatial inhomogeneity, that little density difference will bring down that column of fluid very fast. Along with it, all the particles are coming, so you will call that settling velocity. So, the settling velocity can be incredibly large. Okay. So, that's a mechanism that you just can't go with single particle settling velocity. Single particle settling velocity, in fact, becomes irrelevant. So I earlier was talking about is mining industry and how they want settling ponds. They want all the nasty material to settle down so the water goes to the top. Then they can siphon off. There is some rules about disposing that water, and then you can dredge all those dirty solid, and then you can do something with it. Okay, so making those settling ponds settle fast is a very big deal. So you want to promote these kind of mechanisms for fast settling of particles. Okay. So I want to talk about pseudoturbulence. There are a lot of questions about what is pseudoturbulence, and you may be wondering still what is it. Okay, but I could only do a better job now because what we saw in the past hour is very useful. So it's like a cartoon here. So here there are only 5 particles in this bucket. But let's say all of them are moving in some ways. And each of them have a Reynolds number, maybe 20, 30, 40, 50, something like that. Okay. So each of them have moving relative to the fluid, and they have their little wakes. Now you can scale it up to 50,000 or 5 million particles, each of them having their little wakes. Otherwise, let's say the fluid is not a whole lot of turbulence. Each particle is having a wake. Now imagine that you put a velocity probe in here, and you measure as a function of time fluid velocity or fluid velocity. At that point, as a function, you're going to have a complex signal like turbulence. And this fluctuation, because a wake is passing through you, then another particle comes zipping in a slightly different direction, creating a slightly different wake. Okay, maybe this picture may be too complicated. Maybe this may not be the right thing. Maybe you will have like this. Maybe every time a particle comes, what do you call that? Okay, so it's not classical Kolmogorov scaling turbulence with perfect spectra and things like that. But nevertheless, it is turbulence created by particles. Now, if you are using Euler-Lagrange or Euler-Euler method, you must have some closure models for this turbulence as well. Okay, and this is what I meant as pseudoturbulence. Now, the point I want to make is pseudoturbulence, you can model it in some ways, because pseudoturbulence is nothing but these wakes. These wakes, at least as you see, this is maybe a Reynolds number 50, let's say. Every particle's wake I know. It's just that they come randomly and hit me randomly. Every particle's wake, at least at moderate Reynolds number, is well known. Therefore, first thing is to say is, hey, let me try to understand this wake. Now, one of the things that you can think of, imagine that this probe is there, and it's seeing all kinds of turbulence. Means one way to think of this is, I have a particle and I have its wake. Fixed to probe random particle position is statistically equivalent of fixed to particle, the probe being everywhere. They are one and the same. In other words, I have a probe, and the probe can sometimes be at some spot in the wake, and other times at different spot. So in other words, I can turn the problem around, fixed to probe, and wakes are all over the place. I change it into fixed to wake and probe being everywhere in the wake. They are one and the same. So if I know a particle and its wake, and I can average the flow field, and I say I know now turbulence, I have so that's the technique people have used. So first they say, I want to know what the wake is. So this is a classic graduate level fluid mechanics problem that you may have studied. Now I want to point out that this laminar wake is not this recirculating region. This is what is called the far wake. Okay, so this is like a velocity deficit profile. I don't know how many of you have studied this. So this is the far wake of a turbulent wake. It's actually a laminar wake. So this is the laminar far wake. Okay. So the problem is that you can characterize, given that you have a flow coming at some velocity u infinity, you can precisely characterize. So this velocity, the dip in the velocity profile, has a Gaussian shape. Okay, and this is the axial velocity profile, and this is the radial velocity profile. Everything has been analytically solved. You can do boundary layer theory, free shear layer flow, and you can calculate how does not close to this, okay, not the recirculating, but you go a little behind. What does the laminar wake of a particle looks like? There is an analytical solution. Okay. What I said was earlier that the probe sees every x and every r in this wake. So in other words, if I take this guy and average it over all x and all r, I get mean turbulent measurement by the probe, or the RMS of a probe. Everything, a fixed probe with many different particles, will see it the same as single probe probing every part of this laminar wake. Okay. Well, if the particle Reynolds numbers are a little larger, then you will have, each particle will have not a laminar wake but a turbulent wake. Now, then I have to talk about average over turbulence. So in other words, this is the average, the ensemble average of a turbulent wake. Now, when you average now over all x, so in other, your probe is going to be everywhere. So this is the double average I was talking about. This is the average over turbulence of one particle. But then if I have a fixed probe and the particle is going to be all over the place, then I have to average over all the positions. So I take this and I average this for all x and for all r. I get a double average, which is turbulence wake. Particles could be anywhere, and the turbulence is also random, and I'm averaging over everything. So people have done all this kind of stuff to understand what is the level of pseudo turbulence for a given volume fraction, given Reynolds number, and so on and so forth. Yes?
Is this expression derived using similarity solution?
This is similarity, self-similar solution of a free shear layer wake flow. Okay, so this is the graduate level fluid mechanics. After you study the boundary layer equations, you just solve the boundary layer equation for a turbulent wake, previous one for the laminar wake. So this is the self-similar solution. The center line velocity goes as x to the power minus 2/3. The width of the wake goes as that LW. There is some formula for that. So all of them. For a laminar wake, the width of the wake goes as x, and the center line deficit velocity goes as 1 over x. So these are classic solutions. So we use those classical solutions. Now you can do average over that over the entire spot. So in other words, so this people have done, and so in turbulent case, not only you get the mean velocity. In fact, the mean velocity doesn't matter. It's only the fluctuating velocity in a turbulent flow that matters. So all of them are self-similar solutions that are known, and you can average. So I don't want to give you all the sort of these details are there. So I'm going to skip the details in the interest of time. So what people have done is, earlier what I was talking about is, you take the ith component and the jth component of the laminar wake or the turbulent wake, and you integrate them over the whole volume, and then this factor here takes care of the fact that it's not just one particle, how many particles are there, and so on. And finally, you can predict what the pseudo turbulent Reynolds stress tensor is going to be. Just like you have classical turbulent Reynolds stress, you can see pseudo turbulent Reynolds stress is created, and it has this kind of a very simple scaling relation. So people have developed this. So this gives you an idea about how people, this is if the wakes are potential flow, but the real turbulent problem, you have to stick these things in here, okay, and do the integration over the volume, and there are lots of subtle issues such as convergence and so on and so forth, and people have solved them, and they have found the Reynolds stress due to turbulence. So these are some closures. In other words, if you were multi-phase flow turbulence is dominated by pseudo turbulence, there are closure relations for Reynolds stresses that you can use. Okay. Any questions on that? So this is one approach that people are following these days.